Welcome everyone to This Explainer. When you sit down and interact with a modern language model today, it is incredibly easy to project a soul onto the machine. It honestly feels like there's a sentient being sitting right inside your computer typing back to you. But the truth is actually a lot more mathematical and, frankly, a lot more bizarre. It's mathematically wild that cold, calculated matrices of numbers can be tuned to mimic human angst, or write a coherent sonnet, or even debug your code. So today, our goal is to completely deconstruct this. We're going to look at how these massive AI engines actually learn to generate text.
All right, here's our roadmap for today. First, the magic of next token prediction. 2, preparing the context window. 3, minimizing the training loss. 4, hardware, CPUs, GPUs, TPUs. And 5, scaling AI and its limits. We have a lot of ground to cover, so let's jump right in.
Section 1. The magic of next token prediction. Learning to speak.
Okay, so to really grasp what large language models are doing, you have to understand this one foundational concept: autoregressive models. This essentially means that these models do not output an entire paragraph of text all at once in some sudden flash of brilliance. Not at all. Instead, they build sentences sequentially. Every single value or word is predicted conditionally, based entirely on the previous values that came before it. Think about the contrast between this conditional, step-by-step approach and non-autoregressive models. It's literally a continuous, rolling feedback loop. The model looks at what it just generated and uses that exact information to generate the very next piece. It's a continuous chain reaction. The output from step 1 feeds right into step 2, and so on.
Let's look at a simple example to make this concrete. Imagine the sequence: V, cat, is. To figure out step 4, the model computes a massive probability distribution over every single possible next token in its entire vocabulary. Like, could it be sleeping? Could it be jumping? Now here's what you really need to take away from this. The model doesn't simply predict the next token deterministically. It doesn't just blindly pick the absolute highest number every single time. Instead, it computes the probabilities and then actually samples from that distribution. It's both a sequential process and a probabilistic one. And honestly, that's exactly why you can ask an AI the exact same question twice and get a slightly different answer each time.
Moving on to Section 2, preparing the context window, structuring the data.
Look, you can't just shove the entire unstructured internet into an AI and cross your fingers hoping it learns. The data preparation step is absolutely crucial. We have to take raw tokenized text and split it up into very specific fixed-length sequences. We call this the context window. For instance, a very common early setup was chunking text into strict sequences of exactly 512 tokens. By forcing the data into these fixed windows, we create the essential input-output pairs the model needs. And from a practical standpoint, this context window is exactly why an AI sometimes infuriatingly forgets the instructions you gave it at the very beginning of a long chat. If your conversation pushes those original instructions outside of the window, to the model, they literally no longer exist.
Section 3. Minimizing the training loss, the math behind the magic.
So now that our data is nicely packaged into those context windows, the whole secret to making a deep learning model actually work comes down to one critical thing: the loss. The loss is just the mathematical difference between what the model guessed and the actual, true word hidden in our training data. During training, you can think of the model like a hiker trying to find the absolute lowest point in a massive, multi-dimensional valley. But imagine a terrain with not just 3 dimensions, but billions of them. We call this traversing the lost landscape. And the entire goal of training, the whole shebang, is minimizing this difference.
To really visualize the math happening under the hood here, let's jump back to our cat. Given the sequence, the cat is, the model is assigning actual hard probability values to the next word. It might calculate the probability of the word black as 0.85. The probability of blue is maybe just 0.1, and green is 0.05. Now, if the true word in our training data was actually black, the model did a great job, right? The loss is low. But if the true word was green, the model was way off. The loss is high, and the model desperately needs to adjust itself.
So how does it actually adjust? Well, it tweaks its internal dials, which we call weights. By varying all of these model weights, we steer the whole system toward lower loss using something called stochastic gradient descent. Think of it kind of like trying to perfectly tune a radio, but the radio has a billion different dials. You actually have to use calculus to figure out exactly which way to nudge every single dial simultaneously just to remove the static. The system looks at the current value of the weights and the gradient, or the slope of those weights, with respect to the loss.
This calculates exactly which way to turn those millions of microscopic dials so that the next time it sees the cat is, it gives a slightly higher probability to the correct word.
Section 4. Hardware, CPUs, GPUs, TPUs, powering the computation. Turning millions or even billions of mathematical dials requires an unbelievable amount of compute power. Let's compare the three main hardware architectures side by side. First, you have your standard CPU. It's versatile, sure, but it processes things sequentially, making it pretty slow for this stuff. Then we have the GPU. GPUs are the absolute go-to for deep learning. And actually, it's not because they are inherently smarter. It's because they are highly efficient at parallel processing. While a CPU might do a few complex math problems incredibly fast, one right after another, a GPU can do thousands of simpler math problems at the exact same time. And that is exactly what matrix multiplication requires. Finally, we have the TPU. These are highly specialized hardware accelerators designed specifically by Google for deep learning. They offer extreme speed but require very specific, tailored setups. Finally, Section 5. Scaling AI and its limits. The factory and the reality check.
Because honestly, to train modern language models, one GPU is nowhere near enough. We need thousands of them. But you can't just plug in 1,000 GPUs and expect them to magically work together. You have to choreograph this massive digital ballet. To manage all this hardware, we rely on incredible orchestration frameworks. DeepSpeed helps optimize memory and compute efficiency at a massive scale. FSDP literally shards the model's weights and states across multiple GPUs, so we can train models that are way too gigantic to fit on a single chip. And pipeline parallelism? It splits the model's layers across different devices. It acts exactly like a continuous assembly line, just passing the data from one GPU to the next for maximum efficiency.
But here's the massive reality check. Despite the thousands of networked GPUs, the brilliant orchestration frameworks, and the beautiful math of traversing the loss landscape, remember what this is at its absolute core. Autoregressive models only predict the next token. That's literally it. And because of this fundamental design, they have strict cognitive limits. They do not plan, they do not reason, and they fundamentally do not understand complex logic.
Let's break down exactly what these models struggle with. First off, they have no task-specific knowledge out of the box. They aren't innately built to solve problems, they're just built to predict text. Second, they have absolutely zero long-term planning capabilities. This is exactly why if you ask an AI to write a mystery novel, it might completely forget what the murder weapon was by chapter 4. It doesn't retain a structural memory or a master plan. It is just guessing the next most likely word based on its context window. And finally, they are severely limited in complex dependencies. They sound brilliantly coherent sentence by sentence, but they deeply struggle with tasks requiring strict structural logic. That's why an incredibly advanced AI can sometimes totally fail a classic logic puzzle, like the one with the river, the cabbage, the goat, and the wolf.
So that leaves us with a huge question. We've mastered the art of the context window. We've scaled GPUs into these massive assembly lines. We have minimized the loss so well that computers can chat with us like human beings. But if simply predicting the next word, no matter how ridiculously fast or accurately, can't actually achieve true long-term reasoning or complex logic, what exactly is the next leap required for artificial intelligence? What hardware, or what brand new mathematical concept is it going to take to cross the gap from a really good guesser to a true thinker? Take a moment to let that sink in. Thank you so much for joining me on this explainer, and I'll catch you next time.